Welcome to AP Precalculus 2.12, where we'll be diving into the manipulation of logarithmic functions. By the end of this lesson, you will be able to rewrite logarithmic expressions into equivalent forms. This is a fundamental skill for solving logarithmic equations and analyzing their graphs. We'll be focusing on three key properties: the product property, the power property, and the change of base property. These three rules allow us to expand and condense logarithmic expressions, making them much easier to work with. Let's get started. Our first property is the product property. It states that the logarithm of a product is equal to the sum of the logarithms of each factor. In other words, multiplication inside a logarithm becomes addition outside the logarithm. This property is a direct consequence of the laws of exponents, since logarithms are the inverse of exponents. Let's see an example. How would we rewrite the expression log base 2 of 8x? Here, our x is 8 and our y is x. Applying the product property, we can separate the multiplication into a sum. So, log base 2 of 8x equals log base 2 of 8 plus log base 2 of x. Now, we can simplify log base 2 of 8. What exponent do we put on 2 to get 8? The answer is 3. So, 3 plus log base 2 of x is our final simplified form. This demonstrates how we can expand a single logarithm into multiple terms. A very important application of this property relates to function transformations. It tells us that a horizontal stretch or compression of a logarithmic function is equivalent to a vertical shift. The notes mention that a horizontal dilation of a function f of x equals log base b of x, specifically a compression by a factor of k, is equivalent to a vertical translation. Let's see why. The function for a horizontal dilation is f of kx, which is log base b of kx. Using the product property, we can split this into log base b of k plus log base b of x. Notice that the part log base b of x is our original function, and log base b of k is a constant value. Adding a constant to a function results in a vertical translation. This means that compressing the graph of a logarithm horizontally is identical to shifting it upwards or downwards. This connection between dilations and translations is a powerful insight unique to logarithmic functions, made possible by the product property. We've now seen how to use the product property to expand logarithmic expressions and understand their transformations. Next up is the power property. This property deals with exponents inside a logarithm. The power property states that an exponent on the argument of a logarithm can be moved to the front as a coefficient. This is incredibly useful for simplifying complex expressions and solving equations where the variable is in an exponent. Let's apply this property. Consider the expression log of the square root of x. Note that when the base isn't written, it's typically understood to be base 10. Our first step is to rewrite the square root as an exponent. The square root of x is the same as x raised to the 1/2 power. So, log of the square root of x is equivalent to log of x to the 1/2 power. Now, we can use the power property. We take the exponent, 1/2, and move it to the front as a coefficient. This gives us 1/2 times log of x. We have successfully used the power property to simplify this expression. Just like with the product property, the power property has a significant graphical implication. It tells us that raising the input of a logarithm to a power produces a vertical dilation. In other words, squishing or stretching the function horizontally is the same as stretching or shrinking it vertically. Let's use our example. The function f of x equals log of x squared has the exponent 2. Applying the power property, this becomes 2 times log of x. Comparing g of x equals log of x squared to h of x equals log of x, we see that g of x is just our original function h of x, but multiplied by a factor of 2. Multiplying a function by a constant results in a vertical stretch or compression. This demonstrates that changing the exponent of the argument is equivalent to scaling the entire graph vertically. We've now covered the power property, showing how it simplifies expressions and how it's connected to vertical dilations of a graph. Our third and final key property is the change of base formula. It's a lifesaver when you're working with logarithms that your calculator doesn't have a direct button for. The change of base formula states that any logarithm can be rewritten using a different, more convenient base. This is particularly useful for rewriting logs in base 10 or base a, which are found on standard calculators. The formula says that log base b of a is equal to the log of a divided by the log of b. Notice that the new base is the same in both the numerator and the denominator. We can use any base, but the most common choices are base 10, written as log, or base e, written as ln. For example, let's say we need to evaluate log base 5 of 12. Most calculators don't have a button for base 5. Using the change of base formula, we can rewrite this in terms of base 10. The numerator becomes log of 12, and the denominator becomes log of 5. So, log base 5 of 12 is equal to log of 12 divided by log of 5. Now, you can easily type this into your calculator. When you do, you'll find that the result is approximately 1.544. We could also have used the natural logarithm, ln, which is base e. The result would be the same. Log base 5 of 12 is also equal to ln of 12 divided by ln of 5. This shows that the choice of the new base doesn't affect the final numerical value. We've seen that the change of base formula provides a powerful tool for evaluating logarithms that aren't in base 10 or e. Let's put everything together with a more complex example. Our goal is to expand the following expression using all the properties we've learned. We want to expand the expression, the natural logarithm of a times b, all divided by c cubed. When faced with an expression like this, it's always best to work from the outside in. First, we have a logarithm of a division. The quotient property, which is a cousin to the product property, tells us that the logarithm of a quotient is the difference of the logarithms. So, we can rewrite this as the natural log of the numerator, ab, minus the natural log of the denominator, c cubed. This is our first step. Now let's look at the first term, ln of ab. We have a product inside this logarithm. The product property says we can split this product into a sum. So, ln of ab becomes ln of a plus ln of b. The second term is ln of c cubed. Here we have an exponent, which suggests using the power property. The power property allows us to move the exponent, 3, to the front as a coefficient. So, ln of c cubed becomes 3 times ln of c. And there we have it. The fully expanded form of our original expression is ln of a plus ln of b minus 3 times ln of c. This shows how combining the quotient, product, and power properties allows us to break down complex logarithmic expressions into their simplest components. This skill is critical for manipulating equations that involve logarithms. Finally, let's briefly touch on the natural logarithm. It's so important that it gets its own special notation. The notes define the natural logarithm. It is simply a logarithm with a very specific base. The natural logarithm, written as ln of x, is the logarithm with base e. In other words, ln of x means log base e of x. So what is a? E is a special, irrational number just like pi. It's approximately 2.71828. This number, e, is the base of natural growth and decay. It appears everywhere in nature, from compound interest to population dynamics. That's why the logarithm with this base is called the natural logarithm. So when you see ln x or natural log of x, just remember it's a logarithm with base e. All the properties we've learned today apply perfectly to the natural logarithm as well. There's no new math here, just a new notation for a very common and important base. Let's quickly recap what we've accomplished in this lesson. We set out with the objective to rewrite logarithmic expressions in equivalent forms, and we've done just that. We learned 3 key properties that are the foundation of logarithmic manipulation. The product property allows us to separate the log of a product into the sum of logs. The power property lets us move an exponent to the front as a coefficient. And the change of base formula gives us a way to rewrite any logarithm using a different, more convenient base. We also saw the profound connection between these properties and the graphical transformations of logarithmic functions, discovering that horizontal dilations can be viewed as vertical translations. Finally, we were introduced to the natural logarithm, ln x, which is simply log base e. Mastering these properties will greatly simplify working with logarithmic equations and functions in the future. Thank you for watching.